Okay, so we're going to start here reviewing the factors that affect the rate of reaction and ways to speed up chemical reactions. In the video they cite 5, but actually 2 of them fall under this category, so we'll talk about that in just a second. Concentration or molarity, remember we're talking about the number of particles or moles of particles packed in a certain amount of space. So in this nice diagram here showing you they are equal volumes here, equal amount of space. The higher concentration has more particles. Another way to tell, based off of the numerical value of the molarity, 6 molar versus 1 molar here, you can't really see those very well, but the higher the molarity, the more concentrated it is over time. So more molecules, of course, are going to result in more collision. Also smaller space, like if you change the volume and make it a smaller space, they're going to collide more as well. There we go. All right, so calculating molarity and looking at the equation here and the 2 things in the video. It's always moles divided by liters to calculate molarity. Molarity is a specific measurement of concentration that we use in chemistry. There are other ways to do concentration. There's like percent by volume, percent by mass, molality, any of those things. But for our purposes, we use molarity. AP Chem and College Board only uses molarity, so this is the one that we really go into a lot of detail with. So the moles represent the particles, the liters represent the space. In the video that you saw, does anybody remember what the analogy was for, or one of the analogies that had to do with changing the concentration? Yes, they made the hallways like smaller, right? So making the hallways smaller would be like reducing the volume. So that would be manipulating the denominator here, this one. So making the hallway smaller, making the space smaller, that's going to be manipulating the liters variable here. What was the other one? Does anybody remember? Yeah?
Adding more students?
Yes, packing in more people, shoving more people in the hallways. That's going to be like making it have more particles or more moles. That would be manipulating the numerator here. So those are the 2 ways that you can affect concentration. You can add more particles to it, or you can reduce the volume or the reaction vessel. Now for the calculating part, pretty easy stuff. It's just moles divided by liters. So what does the molarity contain? 0.32 moles of sodium chloride in 3.4 liters. Well, we go like this, put the moles on top, we put in the 3.4 liters on the bottom, and then we just use our handy dandy calculator. Now, doing any kind of calculation means you have to use significant figures. So this is a division problem. We're going to go with the least number. Remember here, this one only has 2 because that 0 in front does not count. That is not a significant 0. And there's 2 on the bottom. So we're really going to keep 2 in our answer. And looking here, this is what I'm getting. And since the number next to the 4 is a 1, I would not round it up. Remember here too, I know we haven't done sig figs in a while, but those zeros in front do not count either. Zeros in front of a non-zero digit are considered not significant. 2 ways to write the unit. You can write it like this with the big M. That's fine. Or you might also see it like this, where it's just moles per liter, and it's a derived unit. You know, like meters per second or grams per milliliter or something like that. So you will see the units written, if you like Google and stuff, big M or moles per liter. Or sometimes they get creative where they'll do this, moles times liter with the -1. You might see it that way too. All right, so that's the basic there, basic calculation. What makes number 2 slightly different? Milliliters. Guess what? You cannot use the equation with milliliters. has to be liters, so we need to convert. Does anybody remember the conversion between liters and milliliters? It is 1 to 1,000, yes. There are 1,000 milliliters equaling 1 liter. Now, I know we always say show your work for everything. However, this is the one time where you don't have to do that. 1,000 milliliters equals 1 liter, so basically you're just dividing by 1,000, okay? And we don't want to waste time, especially with these kind of calculations. So my suggestion is, we're dividing by 1,000. Really, that means we move it 3 decimal places to the left. 1, 2, 3. And then change that to liters, like so. Makes it so much easier. So now we're going to plug and chug. Let's put it in here. We have 0.326 moles, and now 0.25. On the bottom, remember this 0 is not significant. We have 250. Without a decimal, you start from the right. So go ahead and calculate that one. Put my liters in there. Now we have 3 significant digits in the numerator in the moles and 2 in the denominator. So we're going to go with 2 here, least number, because we're doing division. So what is the answer? 1.3, very good. Moles per liter, or you could just put the big M there. That works. Any questions? You guys good? All right, let's talk about the other factors real quick. And I love the little GIF here. Look and pay attention here as when the temperature drops, okay, as you can see, goes, hold on, it's got to go down, maybe. The particles slow down, and as the temperature is rising, they're going faster. Really cool. Temperature is a measure of the average kinetic energy of the particles. Kinetic energy is energy of motion, so really it does make them go faster. Faster molecules with higher temperature. And the faster molecules are going to bump into each other more. That's why you're going to have more collisions. Does anybody remember what the analogy was in the video for this one? It's my favorite one because I always vision what would happen here at Centerville if we did this.
They cut the time in half between classes.
Yes, cutting the time in half. Everybody would be running. It would be hilarious. No, it wouldn't be funny because people would be bumping into each other. Especially not during COVID times, too. But yes, cutting the time in half, having to get to class much faster. Same idea here because that makes people run faster, faster particles. Good to go. All right, surface area. Okay, and here you can see the GIF is in here that shows part of the video there, showing that the students shouldn't travel in packs. We don't want, we want to expose as many particles so that they can collide more. So like a chunk of material versus like powdered material definitely makes a difference in how fast it's going to react. So more molecules exposed, you're going to have more collisions, more likely chance of a reaction to occur. So surface area, you can grind some of the big, large crystals into powder. You can, like for metals, you can like get shavings of them and shave them down. So there is ways to do it so that it will react faster. Catalyst. Catalyst, adding one will speed up a chemical reaction. Now this is the key phrase here as to why. It actually lowers the activation energy. Okay? So we do represent this on our potential energy diagram. Here's the potential energy diagram. As you can see, with the catalyst part, that hill, this part, I'm going to use red, this part becomes a lot shorter. So that decreases our activation energy. And it makes it a whole lot quicker in being able to react. Basically, it's big, complicated kinetic stuff, but it creates a new pathway and it aligns the particles a little bit better so they collide with the right orientation. They don't have to have as much energy in order to react. Remember, activation energy is the amount needed to get it started. So if that's lowered, you don't need as much energy. In our lovely TED Ed, what was the example here, or the analogy for this one? Anybody remember? Was the book dropping and collisions too violent? Anybody at home remember?
What was that, like the teacher?
Yes, hire the matchmaker. Yeah, so basically it aligns the particles better so they're hitting with the right orientation, and that helps lower the energy for those collisions. Because remember, when they're colliding, they have to hit with the right energy and the right orientation so the bonds will break and the bonds will form between the correct elements in the that it's going to be making the new compound. So catalyst here, very important, and we recognize it, and look, you'll have questions referring to the potential energy diagram where you have to remember that it decreases that hill or that activation energy. Activation energy is from the reactant line to the top of the hill or the transition state. So we have one last little practice here. And you'll see something like this also in your assignment. But which picture correctly shows how a catalyst would affect this reaction? Anyone? The middle one, very good. This one would be the one that you would drop and drag. As you can see, the nice little dotted line here showing our hill getting smaller, and therefore a catalyst has been added to the reaction.